we are still in actually part one of the lecture, and I think that from my assessment of the situation is that we should continue looking at the various applications of submodularity before we get into some of the more theoretical constructs, because you can at least get a sense of where it can be applied. So where we are in the first part is well, kind of conveyed by this. You can see it a little bit better on the right. But the next step that the next thing we wanted to look at is to see how, in some sense, a submodular function can be seen as a parameter for a machine learning instance. And before we even see that, let's sort of talk about what do I mean precisely by that. So in general, you might think of like a machine learning problem as essentially saying one where you take some data, you run some optimization problem, and then you get some output. And where the output might be, for example, the result of a learned model. Like the data might be some training data, and the output might be a deep model, which then you could use for doing subsequent decision making. What I mean by a parameter is that it's a parameter during maybe, in some sense, the learning process, or it's a parameter that maybe changes the algorithm in some sense. And I said before, it's very similar to what graphical models did, I think, in the 1990s, where before, people, when they had a particular probabilistic inference problem, they derived it specifically for a particular problem. Whereas when graphical models came along, they said, oh, you just need to run the elimination algorithm, or you need to come up with an optimal elimination strategy. And that sort of abstracted away the problem of actually coming up with an inference problem to one of essentially working on graphs. And so this is a little bit similar, I think, although there are some differences. So a submodular function itself can be seen as a vector in a R to the 2 to the n dimensional space. So let's just zoom in on this. So remember, we were talking about modular functions before, which are in a space of R to the n. A submodular function is an R to the 2 to the n. So it's an exponentially long vector in the set size. And the reason why it's exponentially long is because every single subset, and there are 2 to the n of them, can have its own value. And you might think, oh, well, does that constraint, does the submodular constraint, the diminishing returns constraint, does that basically restrict it? Does that mean that maybe we don't live within this 2 to the this R to the this 2 to the n dimensional space? It doesn't. First of all, it turns out that this is a cone. So the submodular cone is basically the submodular cone within which all submodular functions live. The reason why it's a cone is because one of the properties, which I haven't mentioned, but we're going to talk about ultimately, is that submodularity is closed under conic combinations. So you can take any non-negative mixture of submodular functions and you've preserved submodularity. But the reason why it's full dimensional is because there are instances of where you can take a particular submodular function that lives within this cone, and then you can take a vector in to the Rn, which is itself not submodular necessarily, but there are vectors, none of which are 0, which when you add it to the submodular functions, you haven't lost submodularity in this sense here. So what this means then is that we're really in a 2 to the n dimensional space, and that submodular inequality, the definition hasn't essentially forced us to lie within some subspace or some restricted subdimension of that. So then the question is then, how does this parameterize machine learning problems? So the first one is something where maybe some of you might be very interested in. It's in sort of convex structured norms. And sparsity has become a very important problem in machine learning in the past, I guess, 15 years now, maybe 10 to 15 years. And the basic problem is the following. So let's say you've got some training data. This is probably an instance. This is probably something that you've seen many times over the past week. We've got some training data, which is maybe a set of XY pairs, where X is the input and Y is the thing that you're trying to predict. It's the response. And what you're trying to do is learn some system that learns to map from X to Y. And you can set it up as a risk minimization problem where what you're trying to do is essentially minimize. It's a linear combination of the feature vectors, which is W times X. So W is in an n-dimensional space. X is n-dimensional. And you have a loss function, and you sum over, take the average loss, and then you have lambda times some regularizer, which basically is a smoothness assumption or something that sort of encourages W to be smooth in some way, at least as measured by kappa omega. And there's other variants of that, which are essentially forms of like where you have multiple responses. So there what you're trying to do is you have X and multiple Ys, and you're trying to learn multiple Ws here, each of which is essentially regularized by some omega. Right? So now what you're trying to do is rather than minimizing over just one W, you're minimizing over KWs, each of which is a vector, one for each response. And then the dictionary learning problem, which maybe you've encountered in the past week, is where you're not only, the only thing you get is the responses, where what you get is essentially a set of Ys, like this. And what you're trying to do is to learn the W's and the inputs, learn the dictionary, essentially, learn the things that essentially get composed. And you have one dictionary, which consists of X. But the point is that you have smoothness associated with each one of these problems. And usually what one wants is like if you have a convex loss function of some sort, maybe you're interested in a convex regularizer, convex omega. Now, one particular example is things like total variation. This is quite useful, for example, for image restoration, where you've got a noisy image. Hopefully, it looks noisy on the left. And a particular omega might be, say, the sums of the absolute value of the differences between, say, pixel values. What I've shown here is a one-dimensional total variation regularizer. But in images, you'd have a two-dimensional total variation regularizer, where neighboring pixels have this sparseness property. Now, the sparseness property basically says that you prefer there not to be too many differences between neighboring pixels, right? Because it's sparse, because it's an L1 on the difference, L1 regularizer on the difference. But in general, we prefer convex norms. This is a particular convex norm, total variation. And let's define a little bit of notation. So W is the thing that we're trying to regularize. And the support of W is a binary vector that basically corresponds to an indicator as to when that vector is 0 or non-zero. So in other words, the support of W evaluated at element V is 1 whenever W, the corresponding element of W, is non-zero. So then we can then use a submodular function, which in some sense is an example of this idea of parameterizing a machine learning problem, by essentially penalizing the support of a vector W. So here, basically, W, the submodular function is a complexity measure, right? It measures the complexity of the pattern of non-zeros in the vector W that you're trying to learn. And so the idea is that sparse regularizers like the L1 norm basically says, I want to have as few non-zeros as possible. When you put a submodular function on the support of W, you're saying, well, you can have non-zeros as long as they're cooperative, as long as they cooperate in some sense. Let's take, for example, the ball and urn example. Let's say some of the elements of the vector W are labeled green. Some of the elements of the vector W might be labeled blue. So as soon as you have a green element that's not zero, then it suddenly becomes free. There's no penalty for having non-zero elements for any of the other green elements of the vector. But if you were to add a blue non-zero element, then there would be a penalty. And of course, all generalizations, any submodular function would work with that. Now, in general, when you take the submodular function of the support of W, that's actually hard to optimize. That's not an easy regularizer. In fact, the L0 norm, which just basically counts the number of non-zero elements, already is a hard thing to optimize. But what we can do is the following. We can take the convex envelope of that function. So seen as a function of W, we take the convex envelope of it, which is the largest convex lower bound of this function of W. And that becomes a convex norm in some sense, a convex surrogate for the particular thing that we actually truly want to optimize, which is basically the submodular function on the support of W. And that actually can be obtained via something called the Lovász extension. Now, the Lovász extension is a convex extension of submodular functions. It's a particularly easy one to get. You can get values of it from the greedy algorithm. And I'm going to be talking about the Lovász extension and defining it tomorrow. But for right now, let's just say that it's a convex extension of a submodular function that's easy to get, and that in this particular case, it corresponds to the convex envelope of the submodular function applied to the support of W. And perhaps best of all, it gives you a norm. So that basically means you can use it as a convex norm, a structured convex norm for any particular machine learning problem that you want. And here's by the way, here's the way you get it. So basically, you get the Lavache extension by just running the greedy algorithm. You take UW, you sort it in decreasing order, and then you can get a particular query by evaluating this. It might be a little bit tricky, like I said, we're going to talk about it tomorrow. But any particular norm, any particular submodular function that you use for this problem imposes a different type of complexity penalty on the non-zero entries of W. And then the Lavache extension gives you a convex generalization of that, convex relaxation of that, which can be used for convex optimization in machine learning problems. OK. Total variation, for example, the one that we saw before, just for example, when we did the image restoration, that corresponds to the Lavache extension of a cut function. The L1 norm, raise your hand if you heard of the L1 norm. So the L1 norm is the Lavache extension of a modular function, in fact, of the cardinality function. So even the L1 norm is like, in some sense, a Lavache extension. But with a submodular, with an arbitrary submodular function, you essentially have an unlimited number of convex structured norms that one could potentially draw from and use for your problem. OK. So the next thing I want to sort of talk about is how submodular functions parameterize or generalize information functions. So we saw before that submodularity, like the entropy function is a submodular function. It turns out that any submodular function has this notion of independence. So like, without there necessarily needing to be a random variable. So independence, basically, as seen by a submodular function, means a form of separation or additivity. And so A and B are said to be independent if f of A unit f of B is equal to f of A plus f of B. That's the notion of independence, sort of combinatorial independence. There's a notion of conditional independence, very similar to how in a random variable you can say that A is independent of B given C if there's a certain factorization requirement, or factorization property of the probability distributions. When you're measuring units based on a submodular function, conditional independence of A and B given C requires this equality to hold. And conditional independence and independence need not be the same thing. There's a notion of dependence in the same sense as there's a notion of dependence between random variables. Dependence basically means that this sort of conditional value, the conditional submodularity, which is defined to be f of A union B minus f of B, that has to be strictly less than f of A. So in some sense, conditioning on B has reduced the valuation of A. That's a notion of combinatorial dependence. There's also a notion of conditional mutual information, or combinatorial conditional mutual information, which you can write it in this fashion. Okay. And first of all, it's always guaranteed to be non-negative. Why is it guaranteed to be non-negative? Because when you have a submodular function, the non-negativity of that quantity that I've just highlighted is assured by the submodular inequality. So we've got conditional mutual information. And we also have notions of information amongst sets of data items, sort of generalizations of conditional mutual information, which hold both for the entropic case, but also hold for the general submodular case. So I should mention, by the way, that these definitions, if we were to put entropy as our submodular function, we'd get back exactly the same quantities we know and love, like mutual information, conditional mutual information, information amongst sets of random variables, conditioning reduces uncertainty, all of these things that exist for entropy. But now with a submodular function, all of the same sort of ideas of information and dependence exist, but without there necessarily needing to be a joint probability distribution over the sets of objects that we're interested in dealing with. In the entropic case, the objects we're dealing with are random variables. In this case, we're dealing with any object, data items of some sort. Okay, so with, armed with this thing, essentially we have now a family of clustering algorithms. Unsupervised learning, where we define the sort of combinatorial mutual information, IFAB, which is based on the previous page, basically this thing. And we can consider the following clustering algorithm. So the first thing we do is we partition the ground set into two blocks, A and A complement, that minimize the combinatorial mutual information. Okay. Once we have two block partition, we partition the blocks of the partition again. So basically we partition the first block and then the second block, and then we do the same thing for the complement side. So now we've got 4 blocks of a partition. And we recursively, hierarchically construct a partitioning of the block until finally what we have is essentially a clustering or a partitioning of the objects, each of which has been obtained based on some sort of separation, but where the separation or the partitioning is done so as to minimize one of these combinatorial mutual information functions. Okay. Now this is something that you could do with mutual information, but it'd be very tricky because with mutual information, every particular query requires potentially an exponential time probabilistic inference procedure. Why? Because, just by the fact that you don't know the structure, you don't know what is the best partition, means that you can't assume that there is some underlying graphical model which allows you to do these inferences. The graphical model itself would presuppose the specific structure that you're actually trying to infer. But with a submodular function, it doesn't have the same computational complexity just to do a query. The computational complexity lies within this particular optimization problem. But this turns out to be a special case of a submodular function minimization problem. This is symmetric submodular function minimization. And for this, there are known algorithms. The worst of cases is n cubed. So this is actually something that's feasible. So one way of doing this is to run this n cubed algorithm. It's called Kiran's algorithm. Or alternatively, there's a construct called the Gomerhut tree, which you can form, and then you can delete edges in the Gomerhut tree. And actually, either strategy will be one that, when you do this clustering algorithm, for any submodular function, you will get a clustering that is guaranteed to be no worse than a factor of 2 away from the best possible clustering you can get. Again, thanks to submodularity. But I think this is an example of where every clustering algorithm, or the way that you measure a cluster is entirely different depending on which submodular function you use. But the algorithm is the same, the guarantees get the same, again, thanks to submodularity. Okay, here's another example. This one's a little bit tricky. It'll be a little bit harder to understand, but let's go through it. So first of all, are people familiar with active learning? And are people familiar with semi-supervised learning? Okay, so let's active learning and semi-supervised learning. So active learning in general, here's sort of a very simplified version of active learning. In general, when we have supervised learning, we're learning to map from X to Y, say. And we have Y. We have training data which consists of X, the inputs, and Y, the outputs. In active learning, we start only with the X's, but we get to decide a subset of the labels, a subset of the Y's that we want. Because every time we get a Y, we query, we have to actively go out and try to get a Y. And this is something that actually has real-world implications. Like, let's say, for example, you're doing something like speech recognition or machine translation, and you have a bunch of sentences in one language. Let's say you're doing machine translation. And it costs something to actually get a translation into a different language. And you want to do translation, learn to map from one language to another language. And so what you could do is you could collect a large collection of sentences in, say, one language. Let's say it's Icelandic, for example. And you want to transcribe those sentences into, say, English. But that's a costly endeavor. And so what you'd like to do only is transcribe a subset of the sentences. And so what you could do is then that's the active learning problem. There's 2 ways of doing it. What one could do is sort of in batch, choose a subset of the sentences to transcribe, and then do it. Or there's an adaptive strategy where you transcribe one utterance, and based on the result of that transcription, you choose the next one, and you transcribe it, and you sort of adaptively choose based on the results that you get. So here's an example of a batch active learning strategy where, let's say you've got a graph. In the graph, each node, each vertex in the graph corresponds to a data item for which you potentially want the label for. Okay? So an algorithm, an active learner will say choose 2 items to label. Like for example, here you choose this item and this item. You say, okay, Oracle, please give me the labels for these. Or in the case of machine translation, it will say, please translate these Icelandic sentences into English. And so what comes back is a translation. What the example I'm giving you is a binary classification problem. So the Oracle comes back and says, okay, that one is a plus, and this one is a minus. You can see it if we zoom in a little bit. Plus and minus. Okay. Now what semi-supervised learning is when you start with a set of partially labeled problems. Like here what we're starting with on the left is we don't have all the labels. We've only got some of the labels. But semi-supervised learning basically says, well, infer the remainder of the labels based on the labels that we've got. So active learning and semi-supervised learning should, it seems, go hand in hand together, although these are typically, in the machine learning community, studied fairly separately. I mean, you have papers just on active learning. You have papers just on semi-supervised learning. But here, we're essentially treating them together, sort of simultaneously. And there's not actually very much work on strategies for simultaneous in the form of successive active learning followed by semi-supervised learning, where the active learning strategy and the semi-supervised learning strategy work well together. But that's what we're going to be talking about here. So basically what happens is the learner, then the semi-supervised learner, chooses the set of labels. But then let's say that nature, oops, I don't want to do this. Nature says, okay, this is the real truth, right here on the right. And so the learner suffers a loss. It turns out that 2 labels are gone. Or 2 labels are mislabeled. So this one and this one. And so you suffer a loss, right? And the loss could be seen, it could be measured based on the one norm error between the hypothesized labels y hat and the true labels y. And so that's really just counting. If in the case of binary classification, that's just counting the number of errors that are mislabeled. In this particular example, the loss is 2, because we've mislabeled 2 examples. OK, so everybody got the idea of active learning and semi-supervised learning? OK. Now consider the following crazy objective. Okay. So first of all, gamma of t, this thing in the numerator, is any arbitrary symmetric submodular function. And it turns out that this symmetric submodular function, you can get a symmetric submodular function by starting with any arbitrary submodular function, say f, and you symmetrize it in the following way. So gamma of t is equal to the following way. And the symmetry means essentially, by the way, that gamma of t is equal to gamma of v except for t. So it's symmetric with respect to set complements. And that's true for all t. It's still submodular. It's something that's a property that we need to prove. But I'm giving you that this is still a submodular function. And actually, this corresponds precisely to the notion of the combinatorial mutual information between a set T and the set T's complement. Right? So the mutual information is, in some sense, a form of symmetric entropy. OK, so let's get back to this objective for a second. So we've got this objective. And what we're trying to do is we want to minimize overall T, which is a subset of the complement of L, of this ratio of the information between T and the complement and the size of T. So the claim is that this measures, in some sense, the worst case degree that an adversary can sort of break away a large number of combinatorially independent points from the set that we've labeled. So on the left-hand side here, we can sort of say, OK, suppose we've chosen to label L. OK, so the active learner says, all right, these are the labels I want. OK, but now we evaluate 42. OK, so 42 says, OK, well, you minimize over all subsets of the complement. So in this case, this blue upper region here, that corresponds to one possible t. And what this says is that if it's the case that by minimizing over all such t, that both the numerator, in other words, the information, the combinatorial information between t and the complement is either small, or t, the size of t is very big, or more generally, the ratio of the two is small. And that basically means that the set L I've chosen, the set L I've chosen to label, is a very poor set. Why? Because basically it says that, well, L doesn't touch items that can be very strongly separated away in this combinatorial independent sense from the labels I've got. And so therefore, if the labels I'm choosing are L in the active learning sense, it's going to be very, very it's going to be very, very difficult to inform ourselves about these items in T, because there's a lot of them, and there's a lot of information about those items in T that's not provided by L. So here's another example in the graph cut case. So when it is the case when it's a graph cut, so here's a graph. So on the left, basically, psi of L, so L is the red dots, right? So basically, suppose we've chosen these as essentially a set of things to label. So psi of L is equal to 1/8. And that basically, it's small, right? Because it basically says that there's a large chunk of stuff, namely all these guys over here, that are fairly disconnected. So in the case of the graph cut, basically information, combinatorial information corresponds to graph cut. So basically it says it's fairly disconnected from the things that we've labeled. So that would be a very poor choice of labels, of points to label in a graph-based learning scenario. Whereas on the right-hand side, it's saying, well, here, this particular choice of L, which are these two red dots in the minimum, psi of L is just 1. So it basically says that there's no point that's far away, both informationally, where you have a large group of guys that are informationally far away from the labels that we've chosen. So that would be a very good set of points to label. So therefore, it suggests the following. It says, a good active learning strategy would be to choose an L that maximizes psi. So we want to choose L that maximizes psi of L. Now, suppose we've got L. How do we then do semi-supervised learning? So what we do is, first of all, well, we've got the labels, and let's say we want to agree, those labels that we've got, we don't want to disagree with those because we're assuming those are oracle obtained, those are ground truth. But what we want to do, on the other hand, is we want to choose the labeling that is as smooth as possible, or in other words, the labeling such that we are as informative with respect to the labels that we've got as measured by this combinatorial independence objective. And so gamma, this symmetric submodular function, really is our measure of label smoothness. So here's another way of saying it. I think this really is telling. It's like it sort of corresponds to how much combinatorial information there exists between the labels that we've chosen and the complement. But of course, we still want to be consistent with the labels that we've got. So in order to do semi-supervised learning, we minimize this function. So remember this notion here. Let me just make sure this is clear. So y hat is the labeling. It's the binary vector that we want to label. Y of y hat is the set version of that. So that's just a set. And gamma of that is just the submodular function evaluated on that set. So we want to minimize that thing subject to the constraint that the labels that we're labeling agree with the true ones that we've got. So y sub L are the true labels that we already have. And y hat sub L are the ones that we're inferring, which we're insisting upon being consistent with the ones that we've got. So how do we do that? Turns out, good news, it's an instance of submodular function minimization. We form this particular submodular function. It's only based on gamma, but it's slightly restricted to insist upon those labels that we've already got being positive and the labels that we don't have being non-positive. So it's a restricted ground set. So we never consider ever choosing an element that's not in L, because doing so would either would have the potential for changing a label that is already known. And so the ones that are known to be 1, we insist upon including in the set. The ones that are known to be 0, we never include in the set. And because we're only choosing subsets of V except for L, we'll never violate that. That turns out to be a submodular function. So semi-supervised learning gives us, submodular function minimization parameterizes a semi-supervised learning algorithm. And in fact, when we do choose the graph cut example, it turns out that gives you a very, very standard semi-supervised learning algorithm that was developed and widely used for a while from 2001. The Blum and Schwala algorithm. Is anyone familiar with that? So but now what we've done is we've shown that any submodular function gives you a semi-supervised. Any submodular function minimization gives you a semi-supervised learning algorithm. Okay, so here's the best part. So we said that we wanted to group the active learning part and the semi-supervised learning part. So the theorem we have is that for any symmetric submodular function, which can essentially be a symmetrized version of any submodular function, let's assume that the labeling that we chose does this submodular function minimization problem. So it minimizes the remaining labels subject to the constraint that it agrees with the labels that we got. So then this is the error, and we can put an upper bound on the error of the labeling that we've chosen based on the numerator, which is the inherent smoothness of the true labels, divided by psi of the labels that we've chosen in the active learning setting. So basically it says that by choosing a submodular function, maybe by minimizing over submodular functions, you can get a tighter and tighter bound. And it sort of says something also about nature. It says, like, you find, if you can find a submodular function that sort of agrees well with nature in terms of a smooth, you're guaranteed that you will do well in your active semi-supervised learning strategy, if you can both maximize psi and then do the submodular function minimization. So I think this is a perfect example of what I said earlier, where the submodular function is sort of a parameter to a simultaneous active semi-supervised learning algorithm. And it generalizes many existing semi-supervised learning algorithms and active learning algorithms, but they work together to give you the best of both worlds. Okay, any question about that? Okay, so let's move on. So Bregman divergences are something that are things that are useful in the area of convex optimization, and essentially are parameterized by a convex function. And depending on which convex function you use, you get really useful things like the Kullback-Leibler divergence or the squared L2 norm. And a Bregman divergence is basically, it's not really a distance function, it's a divergence function between two elements. And it's parameterized by a convex function phi, and it's defined in the following fashion. This is actually a generalized Bregman divergence. But the point is that the Bregman divergence between x and y is equal to the convex function evaluated on x, the convex function evaluated on y, minus a subgradient. If it's a differentiable convex function, you just take the derivative evaluated at y, and you take the dot product of that with x minus y, and that gives you the Bregman divergence. And so you have this very, very large family of divergence functions, each of which is parameterized by a convex function. In this generalization of the Bregman divergence, it allows even non-differentiable convex functions. So it turns out that submodularity also has a form of Bregman divergence. There's the submodular Bregman divergence. And for any submodular function, you can define a divergence between discrete sets, which is defined exactly analogously. The only thing that you need is this notion of a gradient map, which is here. Now, it turns out that, as we will see tomorrow, submodular functions surprisingly have subgradients and supergradients, and in fact, simultaneous tight sub and supergradients at any given point. So they're very weird functions in the sense that they're very much not like convex function or concave functions in this sense. And these subgradients and supergradients are very easy to get. And the subgradient map then is when it's the case that there's a choice of different subgradients, it basically just chooses one. So you have this very, very large family divergence functions, the submodular Bregman divergences, which are potentially quite useful, but already they define things like relatively mundane discrete distance functions like Hamming distance. But they also, depending on which submodular function you use, they will give you recall or precision, or they'll even give you back conditional mutual information and other generalizations of Hamming or structured Hamming distances and things like that. So the submodular Bregman divergence is really something that's only beginning to potentially be useful in machine learning for discrete problems. I mean, for things like clustering. And OK, any questions? So we've seen 3 examples of submodularity used as a parameter in terms of convex structured norms, in terms of active semi-supervised learning, and in terms of Bregman divergence. Now, since we're interested in machine learning, it's often the case that maybe we're interested in learning the submodular function itself. Now, in general, learning submodular functions is hard. It's hard in the following sense. Like, if you were to take a training data set which consists of random subsets of the ground set and valuations of that, learning submodularity turns out to be hard. So Goman showed in 2009 that if you only have a polynomial number of queries to a submodular function, then you're not necessarily going to do particularly well with respect to learning a submodular function. And in fact, the worst case is like square root of n over log n in terms of guaranteed approximation guarantee. So you could be quite off from your submodular function if you're just doing a polynomial number of queries. And then sort of similarly, Balkin and Harvey showed that in a PMAC learning setting, it's a particular learning sort of theoretical machine learning setting, that learning submodular functions is not easy. Okay, but these are very, very general learning scenarios. That doesn't really preclude the possibility of learning subclasses of submodular functions, in particular like learning mixtures of submodular functions or learning conic combinations of submodular functions, which is something that is quite possible. So the idea of learning a submodular function in this conic combination is the following. So let's say that we've got a training data set. So x of I, this is a kind of very strange learning scenario because each input is like a ground set, and each output is a subset of that ground set, which is supposed to be good in some way. Like, for example, it might be a maximal set. You can think of this as learning in like learning summaries. Like X might be a collection of images, and Y might be a summary. Or X might be a collection of documents, and Y might be a summary. And a summary, if it's the case that it's evaluated by a submodular function, is obviously going to be something that's good. It's going to be large valued. It's going to have high diversity, high quality, all of those sorts of things. And in general, let's say that we have some parameter W, and we have a score function, which might be a mixture of feature functions. This is the standard sort of structured prediction kind of problem, where I think you've learned about this week, and where this sort of measures the learned sort of agreement between a given x and a given y. So basically, if you have a particular x, and you want to see whether or not a y is good with respect to that, that's essentially this s thing is essentially measuring how good that is. And a decision problem based on once you've learned a function might have the following form, where you have a particular x bar, and you take the maximum over all y. And so the goal is to optimize W, to learn W. And we have a loss function, which measures how well you've done. And so this is the overall loss. It's basically how bad a given predicting of y for a given x is on average over the entire training data set. So this is basically risk minimization. But it's done in this fashion where you've got sort of you're learning subsets of a submodular function. Now, the whole idea of structured prediction is expressed by the following convex optimization problem, where what you're trying to do is minimize a regularized version. This is the regularizer over the weights. And you have essentially a loss psi, which is like slack in the structured prediction case. And you want to essentially make sure that the true guy, W times the feature of the true target label Y, is greater than or equal to the max of the possible predicted minus some slack. And again, the slack is something that you're trying to minimize. So this is the standard generalization of the support vector machine, but generalized to structured objects. Now what we can do is we can sort of express this by solving, by replacing psi with, well, a very simple way of seeing this is that we move psi over here to this side, we move this stuff over here, and now we're minimizing psi, we're minimizing the thing, the thing that psi upper bounds, which is the whole expression here, plus the regularizer. So that's sort of the unconstrained form of structured learning problem with the hinge loss, the generalized hinge loss. Okay, now what's interesting about this is that there's an inference procedure built into the learning process. The inference procedure is, say, doing this maximization. And we could learn this by using a subgradient descent. This is a convex optimization problem. And we could actually learn this using subgradients. Now there's one critical thing here. Like, we're saying that F is essentially a set of submodular functions, or is a conic combination of submodular functions. L we haven't said anything about, but let's assume that it's also submodular. The learning problem is a little bit different because we must have that the W's be non-negative. But this is a convex constraint. The reason why W has to be non-negative is because otherwise we would lose submodularity. Because if you take positive and negative mixtures of submodular function, it's no longer submodular. It would be submodular plus supermodular. But we want to preserve submodularity. What we want to do is learn a submodular mixture. So we need that constraint. But the whole thing is still convex because the positive orthant, this thing here, is still staying within the positive orthant. And so therefore we've got a convex optimization problem with a convex constraint to learn a submodular function. Now there are a number of different loss functions that we can use. In practice, we've found that we can actually find submodular loss functions so that this inference procedure, equation 53, is possible. So this is a submodular maximization problem that's needed within the context of learning a submodular function. Now, this is something that hopefully you've heard a lot of this week, that basically inference and learning go hand in hand. Oftentimes you learn about inference, and we spend a lot of time looking about inference, and you go to machine learning conferences and you see papers just about inference. But then you wonder, well, this is a machine learning conference. Why do they not talk about learning? It's often the case that you need inference to do learning. So if you can do fast inference, you can often do fast learning. So in this particular case, we've got this inference problem, which if it wasn't submodular, we'd get back to this exponential problem again that we saw at the very beginning of part 1. But thanks to the submodularity, this problem can be solved approximately well, the submodular maximization. So I'm going to move ahead because I think we're getting into the details of this. But the point is that each step, we can essentially construct a subgradient based on doing a submodular optimization problem and do very simple first-order gradient descent learning. And you get essentially a subgradient descent learning strategy for learning submodular mixtures. I don't have results for this, but I mean in this talk. But actually, we've used this strategy for learning submodular functions for document summarization and for image summarization. And for document summarization, we have found the best ever reported results on document summarization on 4 standard, widely used corpora. So this really works. I mean, it's something that really, really works well. OK, are there any? Let me pause for a set of questions, because that was a sort of a dense section of the tutorial.
Can you comment on the loss function, like in the previous slide, in which you have submodular optimization plus a loss function.
Right.
And so the loss function, what is the nature of the loss function?
Well, in order for it to be solvable. The loss function itself has to be submodular. So the trick is to construct a submodular loss function, which is also submodular. So in the particular work that we did this for, we were able to sort of take a complement. We have a submodular function, and we take a complement of that function, which is still submodular. And then we maximize that to minimize the loss. And then we add them together. And since submodularity is preserved with conic combinations, we've got a submodular overall objective.
Otherwise, that problem is not.
Yeah, it's this problem here. Otherwise, this problem would be impossible, or just it would be just arbitrarily bad.
I have a question related to this one. So generally, we have some strategies of using some surrogate loss functions to circumvent the issues of non-convex.
Yeah.
So could we have some similar strategies here?
Yeah. Well, the submodularity. So again, like one of the strategies you might assume is decomposability. Like oftentimes, like if it's a Markov chain or something, you can still do inference within this Markov chain. Or if you have some sort of factorization assumption, or you might do approximate inference of some sort to be able to do this optimization problem. It's another map inference problem within the context of learning. The strategy is submodularity that we're using in this particular case. Are there other questions? Okay. So this will be a good time. If you haven't followed what I said in this last section, this is a good time to reset. So everybody resetting? So the next example, I just wanted to talk a little bit about economic applications. Because in machine learning, we're happy with any application, right? We're pretty free and easy with applications. If it's a good application, we'll take it, right? It doesn't have to be vision or speech or anything. And so one application that we might be interested in is economics. And economics, it turns out, is an area where, in which there is a great interest in submodularity because it's a good model for many scenarios. And so one example is consumer costs. So here's one that's very important to all of us, like consumer costs of buying objects. So people are probably aware of McDonald's meal. So the idea of a submodular function is that, the cost of fries and Coke plus the cost of fries and hamburger is greater than or equal to the cost of all three together plus the cost of just fries. Now you might say, well, why is that? Why would that be? In this particular case, when there's only three objects, it's very easy to rearrange terms. We just subtract one from one side and subtract one from the other side, and we get the diminishing returns forms of submodularity. And what that says is that the gain of adding a Coke to just an order of fries, the increased cost of a Coke to just an order of fries is going to be more than adding a Coke to an order of fries and a hamburger. Why? Because oftentimes when you add a Coke to a meal, they'll throw it in for free. It's like McDonald's Happy Meal, right? So the Coke is for free if you buy a hamburger and fries. So that's the submodularity thing. Okay, so there's another construct called shared fixed costs. And this is also something that arises. It's a very interesting model, very simple model, but interesting and widely applicable. So the issue is that costs often interact in the real world. So let's say that we have a ground set of size 2. There's two possible things in the world you might do. So on the one hand, V1 is basically you want to buy milk at the store. It's one action. And V2 is you want to buy honey in the store. It's another action. And there's a cost for buying milk in the store. For any subset, let's say that f of a is the cost of the set A. So let's consider the cost of V1. So the cost of V1 is the cost to buy milk. And so that involves you have to drive to the store, pay for the milk, and drive back home. Okay, that's the cost of buying milk. If you wanted to buy honey in the store, you'd have to drive to the store. There's a cost associated with driving to the store, buy honey, and then cost associated with driving back from the store. That's also a cost. Now, if you were to come up with a cost model, you wouldn't add the cost. If you were going to the store and buying both milk and honey, you would only be paying the cost of driving once rather than twice. So the cost of both buying milk and honey is equal to the cost of driving plus the cost of milk plus the cost of honey, which is less than twice the cost of driving plus the milk cost and the honey cost. So that's called a shared fixed cost. So CD is a shared cost, and it's a fixed cost. So these kinds of shared fixed costs, when you consider things together, some of the costs don't add. They're just included once. And you can, again, think of it like a color of a ball. Like that particular thing, once you've got a blue ball, which is the cost of driving to the store and back, you don't need to pay for that cost again. So it's the shared fixed cost model. So this thing comes up a lot in many different scenarios, of course, a bit more sophisticated. So there's also the notion of like economies of scale, and there's actually different types of economies of scale. There's supply side economies of scale, which is maybe the more typical one that you've heard of. And the question is like, what's a good model for the cost of manufacturing a set of items? Like let's say you're a company and you're interested in manufacturing something, and you have a set of possible things that you can manufacture. Like let's say, if you're a soda company like Coca-Cola, you can manufacture Coca-Cola and maybe Mountain Dew and, I don't know, Dr. Pepper or something. But it would be quite costly for Coca-Cola to suddenly want to start manufacturing laptops, right? Which would require a lot of additional cost. Whereas if they wanted to come up with a new, say, mango-flavored cola or something, maybe they have a lot of infrastructure for producing carbonation and all this other, and sugar and all of the great stuff that goes into soda. And so it wouldn't be that much of an effort for them to manufacture something that involves a lot of commonality with what they're already doing. And similarly, if Apple wanted to start making apple soda for some reason, then it would probably cost a lot for them. First of all, they would probably research it for about 10 years and leak little bits of information about they're coming up with a new cola or something. And eventually it would come out and it would be amazing and we'd all buy it. So, especially me. So let's say that now we have a cost model for a company, a set of things that you want the company should buy. And so here's an example where the things that a company is manufacturing is paints. And so maybe it's manufacturing green paint and red paint and blue paint and all these different colored paints. And so a reasonable model would be to say, for example, the cost of adding green paint to the context, maybe I shouldn't use that color at all. The cost of adding green paint to the context of blue and yellow is going to be less than the cost of adding green paint to the context of where you're just making blue. And why? Because if you're already manufacturing blue and yellow paint, it's easy by mixing them together to start manufacturing green paint. So therefore, it's diminishing returns. It's economies of scale. And that's supply side economies of scale. There's another side of economies of scale, which is demand side economies of scale. And this is a form of network externalities. And this is kind of interesting because here, what the idea is that as the community of a service or an item or a product or a good grows, the value of that good increases. So a very early example of that was something like the railway system in the 1800s, or the telephone. I mean, what good is a telephone if only one person has a telephone? Or what good would Facebook be if you were the only person on Facebook, right? Those are things that one of the things that's so valuable about Facebook is the fact that everybody's on Facebook, which is, in some sense, a network externality. It's something that's extrinsic to the thing that it is. It's how many people use it. So there's something where the value of something increases as the more people use it increase. So that's like a supermodularity. So this is something that's known in economics. It's called network externalities. It was actually defined initially here, but they didn't actually use the notion of supermodularity or sometimes what's called complementarity. It was just sort of defined as a phenomenon. And I think maybe it's fair to say that these guys discovered supermodularity again independently from the work, in operations research and other areas where it was known. So there are lots of examples of this, like Your Education Now, I think, is an example of network externality. Like, why are you here at the Machine Learning Summer School? Because the value that you're getting from this education and from taking this submodular tutorial is going to be dependent on the number of people in the future that are going to use it. And so this tutorial will be more valuable to you if submodularity becomes ubiquitous, and if it's the case that you can say, oh yeah, I took the submodular tutorial at MLSS, and then Google will say, oh great, we will hire you immediately because you took that. See, my goal is to make submodular valuable so that for you it's valuable to learn about submodularity. So this is like co-network externalities, right? So in any event, it seems quite reasonable that supermodularity would be a good model. In fact, it is. For many network externality phenomena, supermodularity is used. OK, so one last thing in part one. I just want to talk a little bit, very, very briefly, about surrogates for optimization. And I wasn't planning to talk in great depth about this. But basically, very, very simply, the way that we do approximate inference in graphical models, or one dominant strategy, is in one form or another, taking a probability model and making factorization assumptions of some sort, either directly or indirectly via an approximation strategy. The idea of a sort of a submodular relaxation strategy is that we take this difficult probabilistic inference problem and we sort of project it in some way onto the space of a submodular problem where we solve it, possibly repeatedly so. So in no case do we make any factorization assumptions. But what we do is, at each iteration, say, we make a submodular assumption. So even though the problem that we're originally solving is not submodular, each iteration we're assuming things are submodular. So it's a very, very different way of doing approximate inference. Because in one case, you're doing factorization, which makes things tractable if it's a tree, say. In another case, you're doing no factorization, but you're doing sort of potential function restriction, which also makes things tractable, but doesn't require there to be limited interaction amongst sets of items, at least in theory. So it's a very different strategy. So obviously, if the potentials are submodular, we can solve them. And if they're not, we can use factorization. I've already said a lot of this stuff. So one thing that it is known is that any function, even if it's not submodular, can be represented as a difference between two submodular functions. And that's an important fact. So any discrete function can be represented as a difference between two submodular functions. In fact, not only two submodular functions, but a difference between two non-negative, monotone, non-decreasing submodular functions. So let's say that we're interested in this particular inference problem for this particular model here, where the energy function is not necessarily submodular. But if it's possible to express it as a difference, and it sometimes is, and if it's easy to, I mean, it's always possible to express it as a difference, and sometimes it's quite naturally expressed as a difference. Like if it's a graph cut with positive and negative weights, we take the positive weights as one submodular function, the absolute value of the negative weights as another submodular function, take the difference, and you get back the original one. That any function, any discrete set function, can be represented as a difference between two submodular functions. And so thanks to that property, if, say, we're interested in graphical model map inference problems, what we can do is, rather than optimizing the energy function, say like minimizing it, maybe we can minimize just the first part, which is an upper bound of the energy function. And we get essentially a submodular function minimization problem, which gives us an upper bound of the true minimization. So it's a form of submodular relaxation. And maybe there's ways of doing this repeatedly. And in fact, there are. There's something called the submodular supermodular procedure, which allows one to repeatedly optimize this by doing this kind of strategy. OK, so that's the end of part one. Are there any questions? OK, so we've seen a lot of applications. One person during the break asked me for some intuition. Is there any intuition for the submodular inequality, the f of a plus f of b is greater than or equal to f of the union plus f of the intersection? So this next section on matrix rank is an attempt to try to give you some very good intuition onto what that means precisely and why it works. Okay. So, and what this will also do is it will define a very special case, but also a very powerful special case of a submodular function, namely the matroid rank function. Okay, so everybody knows what an n by m matrix is, right? So we've got an n by m matrix, and we've got m columns. And our ground set, V, is essentially an index set of the set of columns of the matrix. Okay? Now what we can do is we know what the rank of the matrix is, right? Which is basically, we're talking about the column space of the matrix. The rank of the matrix is basically equal to the number of dimensions spanned by the columns of the matrix. Right? And we can take a subset of that matrix, R of A, where A is an index set of columns, is a subset of columns, and the rank of A, the rank of the index set A, is basically equal to the dimensionality of the space spanned by that subset of columns. That's the rank of the subset. Okay? And so intuitively, and this is an important intuition, that the rank of a set of vectors is exactly the same as the size of the largest linearly independent set of vectors that's a subset of the set A. Right? Number one. Number two, if there are multiple sets of linear independent vectors, and oftentimes there is, all maximal independent sets have the same size. So in other words, if you have one maximally linearly independent set of vectors and another maximally linear independent set of vectors, all of which are subsets of A, they have the same size. Right? Because you can always take one from one and take the other from the other and swap them, and you've got the same size. So here's a particular example. So it's a 4 by 8 matrix. So we've got 8 columns, and we've got a ground set of size 8. Okay? So here's the first 3 columns, A. Right? A is equal to 1, 2, 3. So remember, the sets are indices of vectors. B is 3, 4, 5. C is 6, 7. So one thing to note is like A and B have one column in common, which is vector 3. Right? So this vector is common to A and B. So that we can call this sort of like the common index set is index number 3. It's the common index set because it's common to set A and set B. It's the intersection of the two sets. C is another set of vectors. It's 6 and 7. But the way that this has actually been set up is that vectors 6 and 7 correspond to those dimensions that are spanned both by A and by B. In other words, by vectors 1, 2, 3, and by vectors 3, 4, 5. So in other words, 6 and 7 span dimensions 1 and 2. But if we look at vectors 1, 2, 3, that also spans 1 and 2, and actually more than 1 and 2. And 3, 4, 5 spans 1 and 2, but also more than 1 and 2. So vector C corresponds to the common span. Right? Vector C spans a space that is commonly spanned by vector set A and vector set B. Now AR is just basically is like the dimension. That's the vector that gives A its new dimension spanned not by C. And BR is the vector that gives vector set B its new dimension not spanned by C. Okay? So now if we were to actually compute the rank of A would be 3, right? The rank of B would be 3, because again, the number of dimensions spanned by the vectors B is 3. The rank of the common set, the common span, is 2. Now if we union them together, since C is in the common span of A and B, C is already spanned by A. So therefore adding or unioning together A and C together doesn't increase the rank. Right? We're still rank 3. And similarly, since again C is commonly spanned by both B and A, when we add C to B, we don't increase the rank. If we consider A and any subset of A, that doesn't increase the rank, right? Because we haven't even increased the number of vectors. And similarly, B and any subset of it, we haven't increased the rank. But if we add B, R to A, we've increased the rank to 4, because BR spans a dimension not spanned by any of the vectors in A. And similarly, if we add AR to B, we increase the rank by 1 to 4. Okay? And what is the rank of A union B? Well, that's basically everything. It's the rank of the matrix, which is 4. But what is the rank of A intersect B? Well, that's just the common index, right? That's vector 3, and the rank of vector 3 is just 1. So what we see here is that the rank of the common index, which is A intersect B, is less than the rank of the common span. And for those of you who really want to get intuitive sense of this submodular inequality, this is critical. So just keep this in your minds, that the common index is no greater than the common span. The rank of the common index is no greater than the rank of the common span. All of this stuff together gives us the following, that the rank of A plus the rank of B is greater than, in this particular case, it's greater than, strictly greater than the rank of the union plus the rank of the intersection. So it turns out that this matrix rank problem is a submodular function. In fact, you can define the matrix rank over entries over any field. You can take Galois field 2 or any Galois field P for any prime or any field that you want, and you can define a matrix and you can define the rank over that, and you get a submodular function. So this suddenly gives us, in our arsenal, a very, very large and potentially powerful collection of submodular functions that we could work with just by essentially instantiating it with a matrix and looking at the column spans of subsets of columns. Okay. So any question about this? Could you raise your hand if this is clear to me? Oh, good. Okay. So, question.
What was the last field that you mentioned?
Which field?
You said something, this is generally applicable to any field and not just ranks. And you said
So I'm saying that the entries of the matrix need not be real. I mean, in this particular case, they're just integers, right? But I'm saying that you can use any field you want, any mathematical field, like the binary number, like GF2 or something, anything you want, any field. And you don't necessarily get the same rank function with different fields. So, so A and B are two subsets of column indices. So the rank of the two sets union together is no more than the sum of the individual ranks. So let's look at this with a Venn diagram. So the rank of A plus the rank of B is going to be greater than or equal to the rank of the union. Why? Because there's going to be some common index and possibly common span. Right? And so it turns out that if some of the dimensions, if there is some common span, like obviously if there's a common index, there's going to be a common span. But even if there's no common index, even if A intersect B is the empty set, there still could be a common span because you could have two different vectors. Maybe they're scalar multiples of each other, or maybe they're linearly dependent sets of vectors. They're going to have a common span. So if any time you have a common span, this inequality here is going to be strict. It's going to be strictly greater than. And so what this means then is that the rank function right away becomes a subadditive function. The subadditive function is one that satisfies this property. Okay? F of A plus F of B is greater than F of the union. Right? Subadditivity corresponds to the sum is the whole is less than the sum of the parts. Because the whole is the rank of the union. These sets of vectors have essentially what's called a non-common residual span. And let me just sort of define these things. So let's say that C, just like in our matrix example, corresponds to vectors spanning dimensions common to A and B. So if C is like a common span. Okay, and then AR is going to be something that indexes vectors spanning dimensions spanned by A but not B. So it's like the residual. And BR indices is an index of the vectors that span that in B but not by A. And so therefore, if we look at the rank function, we can decompose the rank into the rank of the common span, that which is spanned both by A and B, and the residual, the stuff that's spanned by A but not by B. So the common span is this, R of C, and the non-common residual spans are AR and BR. Right? It's non-common because AR is spanned by A but not B, and BR is spanned by B but not A. They need not be non-empty. And then similarly, we can decompose the rank of B in this fashion as well. Here's a sanity check question. Need C exist? Must there be a C that has this property? Like right now, I'm just sort of assuming that there is a C. Must there always be such a C? Raise your hand if you think there must be. Raise your hand if you think there need not be. Okay, those of you who raised your hand secondly are correct. So there doesn't have to be a C for a particular rank function, but let's just suppose there is because it allows us to understand the submodular inequality. Okay, so then if we do this, once we add these things together, we have a C, and the C is the thing that allows us to do this decomposition of the rank of A. Because if there wasn't a C, maybe we wouldn't be able to decompose it, because there isn't necessarily an additivity with rank. But when we add these things together, we get that the rank of A plus the rank of B is equal to the rank of the residual span A, twice the rank of the common span, and the rank of the residual span B. So we've counted, by adding things together, the common span twice. But when we look at the rank of the union, we've only counted the common span once. So in some sense, you can think of the common span as being analogous to what we saw in economics. It's the shared fixed cost, if you will. It's the shared fixed span. It's the same idea, right? The rank of C, the common span, is the cost of driving to the store to get milk, right? Not the getting of the milk. But this is true of just matrix rank. And so here we have this scenario, but in Venn diagram form, where we've got the sum of the ranks is equal to so here's the rank of the A residual, which is maybe the cost to buy milk, and the sum of the B residual, which is the cost to buy honey, and the common span. So if we sum the rank of A and the rank of B together, it's kind of like driving to the store twice, right? But if we union A and B together, it's kind of like driving to the store once and buying both milk and honey. So basically, we are charged for the common span, the blue bit, only once. Okay, is everybody with me? Okay, so this is the subadditivity again. So we haven't really said anything different. However, the submodularity comes about from this picture. And this is sort of the critical picture as to why the submodular inequality makes sense. And that's because the common span, C, corresponds to the dimensions spanned both by the vectors A and the vectors B. But remember, A and B need not have any indices in common. The intersection of A and B, we could very well have A intersect B equal the empty set. That could be the case. But it still could be the case that C is non-empty, right? So there is some common span, even when A and B are empty. And so what we see is this picture here, where sort of the common span is represented in the blue, which is the intersection of the green and red, but the common index is the magenta within. And so the inequality is that the common span is never less than the common index. Right? The common index is always rank less than the common span, less than or equal to the common span. And so with that property, we can combine it together by saying that the submodular inequality comes about from this property, where we've got the rank of A plus the rank of B, which counts the common span twice, the rank of the union, which counts the common span once, and the rank of the intersection, which can be no more than the cost of the common span. And so therefore, we have that the blue part here and the magenta part here is never more than twice the blue part there. And that's submodularity. That's the visualization of submodularity. And hopefully that allows you to have a very strong intuition of this. Now this is just the matrix rank function. But all submodular functions have exactly the same form. I mean, have the same thing. You can think of it as a common span. All submodular functions can be seen as essentially being a spanning-like thing or diversity-like thing, like we were talking about earlier. Rather than delving into this Matroid example, which I think will take us more than 10 minutes, I'm going to actually skip. What I had actually planned as part of part 2 was I'll just tell you briefly what we were going to do, which will only take 30 seconds. Okay, so the matrix rank problem that we just saw obviously gives us a submodular function. But there's a more general construct called a matroid. And what a matroid does is it's essentially an abstraction away from some of the properties that exists in matrices and properties of independence of vectors independence of column vectors in a matrix. And it, in some sense, gives us something called a matroid rank function, which is also submodular. But what's interesting about matroids is that you can talk about matroids without talking about matrices. For example, you can talk about graphic matroids, where basically the rank function comes from spanning trees in a graph. You can talk about partition matroids. You can talk about transversal matroids. And there's lots of different matroids. And matroids are important for two reasons in submodular optimization. On the one hand, they give us a great deal of intuition about what submodularity is, thanks to the matroid rank function. And even the matrix rank function that we just saw gave us some intuition. Number two, matroids are a larger family of algebraic objects than just column spaces of matrices in any field. So there are matroids that don't correspond to any matrix. Three, matroids give us essentially a set of constraints that we can do submodular function optimization on. So let's say we have a submodular function and we want to optimize it subject to a set of matroid independence constraints. Those are solvable problems and are very useful for machine learning. And matroid constraints, on the other hand, are very, very flexible and powerful. Like, for example, you can generalize things like matchings, and you can do, like we worked ourselves on a problem that involved alignment in machine translation between two languages. And it turns out that turns out to be a submodular optimization subject to a matroid problem. So we won't have time to talk about that. Let's talk a little bit more about submodular functions. But I do suggest everybody look at that section in the slides, which you will have at some point. So, okay, so let's do a little bit more on just submodular properties. So first of all, like, where does the name submodular come from? So I thought this would be kind of fun to talk about. So the notion of submodularity actually comes originally from lattice theory, sort of Birkhoff lattice theory. And it in particular corresponds to the height function of a lattice. So a lattice is basically an algebraic object of some sort, where you have a set of elements. And each pair of elements has a join and a meet. So basically, it's usually depicted in this. So if we have two elements, let's say these two elements, then the join would be this element and the meet would be this element. And we can actually measure the height of any particular element in these kinds of diagrams. So the height function, for example, like these guys would be of height 3, these guys would be height 2, and this is of height 1, and this is of height 0. So we can say the submodularity of the height function corresponds to basically the height of x plus the height of y being greater than the height of the join plus the height of the meet in the lattice, which is actually true in this particular lattice. And it's true for all lattices that are called upper semi-modular. And so upper semi-modular lattices have submodular height functions. And then lower semi-modular lattices correspond to supermodular height functions. Now the name seems to be a little bit reverse of what you'd think, but actually that's where it comes from originally. Okay, so let's get back to the submodular definition. So here's our definition of submodularity, which we now know. Now, interestingly enough, it's often the case that in fact, many papers do this almost implicitly, where you just assume that the function, the submodular function, is normalized. And normalized means that basically f of the empty set is equal to 0. And if it's not normalized, you just subtract off f of the empty set. That's a pretty innocuous thing to do because it doesn't change the minima, it doesn't change the maxima, and it makes a lot of the algorithms simpler to reason about. And it doesn't really change the flexibility. So oftentimes, we'll just implicitly assume that things are normalized. But what is perhaps more interesting is that any arbitrary submodular function can be represented as a monotone, non-decreasing submodular function and a modular function. So first of all, a Polymatroid function is a submodular function that is normalized in the sense that f of the empty set is equal to 0. And it's monotone non-decreasing. And that basically means for all sets that are in this relationship, meaning A is a subset of B, f of A is less than or equal to f of B. So if f is normalized, monotone non-decreasing, and it's submodular, then it's called a Polymatroid function. Now, all submodular functions, even if it's not a Polymatroid function, can be expressed as the difference between a Polymatroid function, f bar, and a modular function. Now, why is that? Well, the way we can very, very simply see this is by defining this modular function to have these gains. And let me write this, what this actually means. This is equal to f of v minus f of v except for a. So this is like a gain. It's like the gain of adding a to the set which consists of everything except for a. So this is the set which consists of everything except a, and we're adding a to that set. And thanks to submodularity, thanks to diminishing returns, that's the biggest context we could possibly add a to, right? So that's everything except for a. The context cannot get any bigger without actually also including a, in which case obviously the gain is going to be 0, right? So when we take the modular function to have entries here, we're saying that the modular entry for a is the smallest possible gain for a that can exist in the submodular function. And so what we're doing is we're then subtracting off these gains. Okay? So we're forming this f bar. This is f bar here. So f bar is equal to f of a minus the modular function on a, where the modular function is defined to be the sum of the smallest possible gains. So the claim is that f bar is a Polymatroid function. The reason why it's a Polymatroid function is because when we look at the gain of f bar, right? Well, just by definition, that's equal to the gain of f. That's the gain of a in the context of gain of lowercase a in the context of uppercase a of f, minus that one entry for a. And thanks to submodularity, this is always going to be non-negative, right? Because we're taking f of a except in the context of a minus f of a in the context of the biggest possible gain. We're subtracting something which is guaranteed to be no larger than the thing on the left-hand side. So that's going to be non-negative. And so therefore, this function is always going to be, f bar is always going to be non-decreasing. Okay? So f bar is what's called the totally normalized version of f. Now, reason why I think this is interesting is because it basically says that all of the structure, all of the interesting interaction, all of the way that we talked about, like the shared fixed costs or the complexity or the way things sort of talk to each other in a submodular function, is captured by the polymatroidal component within a submodular function. Okay, so you can, when you're interested in talking about interaction, the way two items diminish their returns or share their costs, one can talk about that identically up to sort of this modular offset. Now, one thing one can do is just is define polytopes based on this. And so this is something that we're going to talk about a little bit about more tomorrow. But basically, this polytope, which is basically a subset of the n-dimensional space, is guaranteed as a result to be in the non-negative orthant. So it's going to look something like this in R2. The other thing you can look at it is like when you, for example, you're doing, like here's a practical thing, like when you're doing graph cut-based image segmentation. So remember we had our unary potentials and we had these submodular potentials. What this is saying is that there's no reason for doing graph cut-based image segmentation to actually have anything more than monotone non-decreasing submodular functions, namely Polymatroid functions for our pairwise potentials. Why? Because the unary potentials are like our modular function. So that essentially means that the whole energy function can be potentially an arbitrary submodular function just by having the unaries capture the negative and the positive stuff. Whereas the pairwise stuff can be all strictly monotone non-decreasing, non-negative submodular. So it allows us to concentrate our focus on interaction where we need it to be concentrated. Okay. A couple of other bits of notation. Or maybe we're running out of time for today. Are we running out of time? Okay. There's a lot more stuff. Okay. So are there any last questions? So I guess tomorrow we're going to talk more about theory and algorithms. So I'll try to, given what we've skipped today, adjust tomorrow's lecture so that it's not based on knowing a lot about matroids, because we didn't get a chance to talk about it.